Hi students, welcome to another video on Bode plots. Okay, let us see the initial slides of this. So we should know these things. Make sure that you are available with full concentration. Okay, let us kickstart with. Okay, now we are supposed to plot a Bode plot for this particular transfer function, especially the magnitude plot, and we need to find out what is the stability of the system, that is typically to find the gain margin and phase margin of the system. First and foremost thing is that we have to convert this into time constant form. When I say time constant form, so it should be in the form of 1 plus s tau, and the coefficient of s power 0 here should also be 1, meaning I have to take out 25 out from this. So since it is already in s plus 1 form, that is here the tau is equal to 1, this is already there in the time constant form, whereas this is not in the time constant form. I have to take out 25 out from this. So when I take 25 out of this quadratic equation, it will become s square by 25 plus 4s by 25 plus 1, and this is s plus 1, and on the numerator I have 25 only. So this is the transfer function I end up with after converting this into time constant form. So I can now basically write what is h of gfs into h of s in the time constant form for this particular original equation. So this 25 will go with 25. I will end up with 1 s plus 1, so it will be s square plus s square by 25 plus 4s by 25 into s plus 1. So for this we have to plot the Bode plot. So of course we know that, okay, how do we plot this? Of course, first and foremost thing is that we have to find the magnitude at origin. So let us assume that the origin origin frequency as 0.1 radian per second. Since it is 0.1 radian per second and the terms contributing at the origin is only this k, if you can see this, since k is equal to 1, so in this case since k is equal to 1, we will be writing the magnitude at origin as equal to 20 log of 1, which is equal to 0 dB. So the magnitude at the origin is 0 dB, and we can write the slope table here. So let me write the slope table. Slope table for this is, so let us list all the terms. So here it is. So you have terms, you have the corresponding cutoff frequency, you have the individual slope, and you have the resultant slope of the entire system. So let us list all of them for the given transfer function. So we have the terms as 1 by s plus 1, its cutoff frequency is 1, and its slope is minus 20. Of course, let me write it as dB per decade here. This is also dB per decade. This cutoff frequency is radian per second. So this minus 20 dB will going to continue after 1 radian per second. So next you have term. So maybe while writing here, so you can write it as s square plus 4s plus 25. This will not actually alter the calculation of cutoff frequency, all those things. Cutoff frequency is actually omega n for this particular quadratic equation. So in which case omega n square is 25. So omega n happens to be 5 here. So second cutoff frequency is 5 radian per second, and this has got a slope of minus 40 dB per decade as the individual slope after 5. So overall this will become minus 60 dB per decade after 5 radian per second. If you want to write the magnitude and phase equation, so let me write the Okay, let me write the magnitude equation. Maybe for writing the magnitude equation, you can still consider this form itself, so that I can write. So this is magnitude is equal to 20 log 25 minus 10 log 1 plus omega square minus 10 log. So what is the real part? Real part happens to be 4. Real part happens to be, okay, suppose if you replace this s by j omega, so can I write this as, so how can I write it? Is j omega whole square plus 4 j omega plus 25. So this is, I'm just writing only this. So will it not become 25 minus omega square is the real part, the imaginary part happens to be j 4 omega. So the magnitude of this happens to be under root of course 1 over under root of 25 minus omega square whole square plus of 4 omega whole square. In terms of dBs, this will be minus 10 log of 25 minus omega square whole square plus 4 omega whole square. So this will be the magnitude, so that I can write it here. So this is minus 10 log 4 omega whole square plus of 25 minus omega square whole square. This is whole square magnitude. So this is the magnitude of this particular term. So I am just rewriting this as it is. So this is required for plotting the graph. So don't get confused while plotting the graph over here. To plotting the graph, I am just taking it. So whereas magnitude, all those things you can use the same equation. So now what is the phase equation? So if you carefully observe, phase equation has got two equations. So it is now minus tan inverse of omega, and if you can see here, these are the two terms, the real part and the imaginary part. So the angle becomes minus tan inverse of, here it is imaginary by real, so imaginary is 4 omega, real part is 25 minus omega square. So this is my phase equation for values between 0 and 5, between 0 and 5, okay, you can between 0 and 5. So this is what the phase equation between 0 and 5. After 5 I cannot use this equation. So after 5 this equation is replaced by phi is equal to minus tan inverse of omega minus of 180 degree minus tan inverse of 4 omega by omega square minus 25. This is the equation. So this is the equation for values of omega greater than 5 radian per second. See now, so we have two equations for this phase equation. One is for values between 0 and 5, and for values greater than 5 I have to use this equation because the denominator here becomes minus. So you cannot simply take this minus and then make it plus here. So there should be a separate equation for phase of this plot for values of omega more than 5. That is more than, because when it becomes more than 5, this quantity will become negative. So when it will become negative, so I have to use this equation. So it will be 4 omega by omega square minus 25. So let us try to plot the graph, and let us try to find omega PC, omega GC, and ultimately the okay, let me just take this graph sheet now. So let me start marking the points. So if you can see here, magnitude at the origin is 0 dB, so that I can start from the top as 20. So this is now 0 minus 20, this is minus 40, this is minus 60. Okay, what I'll do now is, so initially you can see the magnitude at the origin is 0 dB. It will be there till 1 radian per second. So let us take the magnitude at the origin as, phase is 0.1. It is 1, 10, 100, 1k, 10k. This is omega in radian per second. Now if you see this table, so this table says the magnitude at the origin is 0 dB. So let me write this 0 dB till the first cutoff frequency. First cutoff frequency is at 1 radian per second. I will write it this till 1 radian per second. After 1 it goes with a slope of 20 dB per decade. So what I'll do is, so instead of doing 20 dB per decade, let me do it 6 dB per octave. So 6 dB per octave is nothing but 20 dB per decade. I'll do 1, 2, 3, that is now it is 6 dB down, and I'll go by 1 octave. So what I did here is, so I just came down by 6 dBs and went by twice the frequency. Now this is actually 20 dB per decade, which is nothing but 6 dB per octave. This will continue till 5 radian per second, because at 5 it's a different slope. So now I will stop it at 5. So now this is, I'm stopping at 5. So after 5, so what is the slope of this? This is minus 20 dB per decade. Now then what is this frequency now? So this frequency is 5. You can see the next cutoff frequency is 5. Afterwards the slope is minus 60 dB per decade. So for doing minus 60 dB per decade, I'll do it. So it is 18 dB per octave. So I'll come down by 18 dB now. So it is 2, 4, 6, 8, 10, 12, 14, 16. Now I'm almost there at 16. Next it is 18, and I have to go 1 octave. Octave means twice the frequency. Now this is actually 18 dB per octave. If I write it, this will be 60 dB per decade line. So this is 60 dB per decade line. So I can write it till the end. So here it is minus 18 dB per octave, or minus 60 dB per decade. So we have plotted the graph now. Next we need to find what is omega GC, omega PC. So if you can carefully see here, omega GC is the frequency at which it crosses 0 dB. Can you see this is 0 dB and it is crossing 0 dB at 1 radian per second. So let me repeat, here it is 0 dB. Where it is going less than 0 dB, is it not happening at 1 radian per second? So this is 1 radian per second. Using, of course, from the graph, omega GC happens to be at 1 radian per second. Okay, this is omega GC. So can we find what is omega PC now? Now we have two equations. Which equation to use to get omega PC? You can see this is one equation, this is the other equation. If you carefully observe, so what I can do is, so let me just give values, different values of omega, and find the phase of it. So what are the phase equation you have? You have the phase equation as minus tan inverse of omega minus tan inverse of 4 omega. Okay, let me write it here. 4 omega by 25 minus omega square. Other equation is minus tan inverse of omega minus of 180 degree minus tan inverse of 4 omega by omega square minus 25. These are the two equations. So this is for values of omega between 0 and 5, This is for value of omega greater than 5. So let us give different values of omega and find the, if it is 0 and infinity. If it is 0, what is the phase? You can see it is 0 degree. If it is infinity, see what happens here. If it is infinity, so will you have this as minus 90? Will you have this as minus 180? So what is this? This is tan inverse of infinity by infinity square. So which is larger now? Is this larger? So when this is more and more, can I write it as this approximately equal to 1 over infinity? So is it not 1 over infinity is 0 and tan inverse of 0 is 0? Is it not minus 90 minus 180 minus 0? Is it not minus 270 degree? So when omega is infinity, this phase is minus 270 degree. So we are looking at what frequency this becomes minus 180 degree. So that frequency is omega PC, correct? So I need to find this. So now we have these two equations. In which equation you may get this omega PC? Either this or this. I will say it is in this equation, that is in the second equation, for values of omega greater than 5 only you will get this omega PC, because you may get this 90 degree at omega is equal to 5, but this is not giving 90. So since at omega equal to 5 it is less than 180 degree, so for values of omega greater than 5 only you will get minus 180 degree. So let me use this equation and find what is omega PC. So what I do here is I use the equation, second equation, try to find out. So let me just carefully do it. It is minus tan inverse of alpha A minus of 180 minus tan inverse of 4 alpha A divided by alpha A square minus 25, close the parenthesis, I think that's it. So now let me equate this to alpha equals to minus 180. Shift cal. So let us see at what frequency I get this. You see now it is at 5.38. So omega PC is coming out to be 5.38 radian per second. 5.38 radian per second is the omega PC. Of course, if you want to verify, you can just verify. So what you can do is you can take out that equate it to minus 180. So what I'll do is I'll take out this. I'll calculate for 5. You can see. Oh, sorry. So okay, for 5 it will, since it will become 0 there, so let me do it for calculate for 5.01. Can you see it's around minus 168? So let me now do it for calculate for 5.1. Can you see it is minus 171? So let me do it for calculate for 5.38. Can you see now it is minus 179.8, so which is close to 180 degree. So omega PC is 5.38 radian per second. So this is omega PC. So now that omega PC, I'll just mark it here, it is 5.38. So is this somewhere here? This is 5. So let me just mark it slightly below that, maybe somewhere here. So this is from 0 dB. From 0 dB, how far it is? This is my gain margin. So what is the gain margin? If you actually count this, so 5.38 is almost equal to 5. Can you see this is 10, 12, 14, almost close to 16 dB is the gain margin. Actually here magnitude is minus 16 dB. So gain margin happens to be minus of minus. Of course, gain margin is actually equal to negative of the magnitude at omega equal to omega PC. So the actual magnitude what you have is minus close to minus 16 dB. So it is minus of minus is 16 dB. This is from the graph. Maybe you can also find using this omega PC, you can find what is the gain margin. So what I'll do is I'll use this equation and try to find out what is the magnitude at 5.38 radian per second. So I have this equation, which is now 20 log 25 minus 10 log it is 1 plus alpha a square minus 10 log 4 alpha a square plus 25 minus alpha a square whole square, close the bracket. Calculate for 5.38. You can see magnitude is minus 13.6. So using calculation also, what is that I'm trying to do? Magnitude at omega equal to omega PC is, from the equation it is minus 13.6 dBs. So what is gain margin then? Gain margin is negative of the magnitude at omega PC, which is nothing but minus of minus 13.6, which is plus 13.6 dBs. This is okay. This small variation here, this is not exactly 16, maybe slightly less than 16, maybe 15 dBs. Okay, this is an asymptotic plot. This is an approximate plot. This is an approximate asymptotic plot. This is the exact one. So 13.6 dB is the correct value in terms of magnitude. This is also perfectly right. This is asymptotic value of gain margin. So once we found gain margin, we need to find what is the phase margin of the system. So phase margin is nothing but 180 degree plus the phase at omega GC. So what is omega GC? Omega GC is actually how much? This is 1 radian per second. So omega GC is equal to 1 radian per second. So you substitute in this phase equation. So which phase equation to choose now? So you have to choose that equation which is applicable for value of omega 1, which is the first equation. So I will use this first equation, find out what is phi at omega GC. So is it not minus tan inverse of alpha A minus tan inverse of 4 alpha A divided by 25 minus alpha A square, close the parenthesis, calculate for 1. Can you see it is now, okay, this is phi of omega GC is minus 54.46 degree. So this is my omega GC. So what is in phase margin? Phase margin is given by so now it is plus of 180. Can you see it is 125 degree? 125 degree is my phase margin. This is while taking omega GC as 1, which is from the plot. You can actually find what is omega GC from the equations. Where you are equating this magnitude to 0. This magnitude can be equated to 0 to find omega GC theoretical, that is using the equations. Whatever omega GC we got here is 1 radian per second is an approximate and asymptotic value. Graphically this is perfect. So graphically we have a gain margin of 16 dB and a phase margin of 125 degree. So over here from theoretical calculations, the gain margin is coming out to be 13.6 dB. Okay, let me write it here. Its counterpart using the equation is 13.6 dB. Let me find out what is this, because we got from the plot omega GC as 1. Let me find out what is omega GC using the equation. So what I'll do, I'll feed this equation equated to 0. So now can I write is 20 log 25 minus 10 log 1 plus alpha a square minus 10 log again 4 alpha a whole square minus 25 minus alpha a square whole square, close the parenthesis. Okay, I need to put one more parenthesis. Is it fine? I think that's fine. That should be equated to 0. Have I equated to 0? Okay, let me equate it to 0. Okay, this is alpha equals 0. Shift cal. I'll get omega GC. So from plot we got it as 1. Let us see theoretically how much we'll get. It will be slightly less than that, but it is very close to that. Just waiting for omega GC. Okay, when it says can't solve, so what I'll do here is, okay, let me not equate it to 0 now. Oh, did I not mention 20 log 25? This is 20 log 25 minus 10 log so and so minus 10 log. Okay, now what I'll do is, let me just don't panic. Let me make this 0 and then say calculate for 0.01 what much is the magnitude. Oh, there is some math error. Maybe let me close one more parenthesis, calculate for that. Oh, some issue. What is that? 20 log 25 minus 10 log of 1 plus alpha square minus 10 log of, open the parenthesis, 10 log 4a square. Oh, this would have been plus. Sorry. This is plus. Okay. Now let me alpha equals 0. If you get a syntax error, I need to, okay, that one more parenthesis I should remove there. Okay, I'll remove this. Shift cal. Now it should give omega. There I made a mistake while editing. This I made it minus. Okay, now this is coming out to be 0. Let me just check out. So okay, let us clarify ourselves. Calculate for 0.001. Can you see it is started here itself? Now maybe when I calculate for 1, okay, now theoretically speaking this has gone below 0 here itself, but asymptotically it's here, but it's happening over here for a theoretical value. So you can take omega GC as 0. When omega GC is 0, then what is the phase? Phase is actually 0. You can see omega GC theoretically becomes 0 radian per second. Then what is phi at omega GC? This is 0 degree. Then what is phase margin? Phase margin is actually 180 degree plus of phase at omega GC. This happens to be 180 degree itself. So now we saw that this was 125 degree from graphical, so this will become actually 180 degree. So maybe let me just clarify this in the MATLAB code also. Let me just do that for you. Where is this? Okay, let me open MATLAB. These are some interesting problems where you will get things to learn by doing both graphically as well as using calculation, and you have the MATLAB tool for verifying your answers. So what I'll do is I'll go here, okay, this MATLAB, I will use my earlier code. Let me edit this. So we will be getting this 180 degree and so on. So okay, let us just wait for, let me take one of the variable, so one of the transfer function which we already have, Control C. I will copy paste. So what are the transfer functions? So let me just edit in this time constant form itself. So this is now 25, this is okay 1 4 25, and then this is 1 and this is 1 here. Okay, that's it. We have 25 s square plus 4s plus 25. This is 1, this is s plus 1. If I run, let us see what I'll get. See now, see here, is omega gc is equal to 0, which is exactly we got it here. See now, we got omega gc theoretically as 0 here. See, is this omega gc 0 theoretically? So using equation, we got this as what? Omega gc in graph, we took it as 1 radian per second, because we took this as 0 dB till 1 radian per second. After 1 only this was coming, because this is asymptotic plot. But if you take the actual plot from the origin itself, it starts deviating from 0. So that's why it goes below 0 even at just greater than 0. So that's why omega gc is 0 theoretically. So theoretically omega gc is 0. So that's what we got it from the equation also. That's what we got it from the equation also. Now that's why, so that's what your MATLAB also clarifies. You can see omega gc is 0. Can you see what is omega pc? Omega pc is actually how much? This is 3.52 degrees. So this is my 3.52 degrees. So this is the value what you have, and you can see what is gain margin. Gain margin is 4.8. So what is 4.8 in dBs? You can see the 4, it is 13.6. Can you see we got it as 13.6 only? Can you see this is 13.6 only here? This is 13.6 is your gain margin, and of course phase margin is 180 degree. Phase margin is 180 degree. This is, I don't know why it is coming as minus 180 degree. Actually this is because when it is 0, this phase is not contributing, this is not contributing anything, because this is, of course, this plus or minus 180 is same. So that's why just maintain it as minus, but if you can see here, this is 13.6 so and so, and this is minus 180. System is stable. System is stable here because you have a gain margin of this much. Gain margin of this much. So this is actually plus 180 only. This is plus 180 degree only. Okay, if I just make this 20, let us see what happens. If I make this 20, then you can see this is okay. Omega gc is not at all there. If I make this 30, then you can see this phase margin is becoming positive. So which means there also it was actually 180 only. This is not okay. That was not minus 180. That's actually plus 180. Because when I increased it, the phase margin slightly reduced. Of course, the gain margin was also reduced from 13.6 to 12 dBs. So please note that this phase margin, if I substitute this as 25, when I make this as 25, here in calculation we got the phase margin as what 180 degree in actual value, that is using calculation, which is 180 plus, because this phase is equal to 0 degree. So whatever you are getting for this 25, this minus 180, what you are getting is not correct. This is actually plus 180 only. So that I just verified by slightly making this more. Instead of 25, if I make it just 30, so then you can see phase margin becomes of course slightly reduced from 180 degree to 136 or so on. So you can do one more thing. Suppose if I increase this gain by this much time, that is 4.8. What is 4.8 multiplied by 25? 4.8002 multiplied by 25, sorry, is actually equal to 120. If I make it 120 here, you can surprisingly see phase margin, gain margins will be 0. See now, this is almost 0 degree. This is e power minus 6. Can you see gain margin 1 means it is 0 dB. Interestingly, can you see omega PC, omega GC both are same. This is omega GC, this is omega PC, both are same. This is the condition of oscillation. Can you see it is almost okay? This is coming out to be, this is of course I don't know why this gain margin is coming like this, but it is actually 0, because 1 means okay 20 log of 1 is 0 dB. So this is 0 dB, and whatever you have, let me just run it again. Okay, this is not 292 dB, this is actually 0, because here you can see the gain margin is 1, 20 log of 1 is so and so. Okay, this way you need to clarify whatever theoretical and simulation wise, and the asymptotic values should match each other, and if there are any slight variations, so we should be confidently say okay what you are getting is close to the expected values. Thank you.